have a challenge for all of you. And please do not skip this video. This is not a Mr. Beast Honey ad. So let's get into it. I want you to read out the numbers that you see on this screen and take a minute to pause this video, read out the numbers, and unpause once you're done. So hopefully you should have gotten the numbers 33981 21293. But let's try something harder because this one was probably a bit easier for you. So these are clothing items, and I want you to read out the clothing items that you see. So pause the video again and unpause once you're done. You should have probably gotten something along the lines of a shoe or a boot, a t-shirt, pants, pants, t-shirt, pants, hoodie or shirt, shirt, sandal, and shoe. So this was probably easy for you. I'll tell you that. But then there's some people who don't find this easy. And by some people, I mean computers. No joke. So computers can actually classify all sorts of images. They can classify images like these handwritten digits, and they can even classify images like clothing items. And not only this, they can be used to classify all sorts of images and even classify and diagnose diseases. Like, this is crazy. And so, driven by curiosity and ambition, I decided that I wanted to make two projects where I wanted to train two feedforward neural networks, one that could classify these handwritten digits, and two that could classify clothing items. So, first of all, let's backtrack. What even is a neural network? And what is a feedforward neural network? So, a neural network is essentially connected layers filled up with neutrons. And these are called neutrons, or you can call them nodes as well. So in a neural network, it starts off with an input layer. So these are the input layer, and they get specific information from the data sets. And then we have the output layer. The output layer predicts the final outcome that you get from the input layer to the output layer. But then there's something missing, and those are the hidden layers. The hidden layers are the layers that are actually performing the computations that take the input layer to the output layer. And if you have more than one hidden layer, it means that your neural network is deep. Now, what I have are two deep neural networks, and these are feed-forward neural networks. This means that it only goes in one direction, forward. So it goes from the input layer to the output layer. And let me go a bit more in detail onto what the input layer and the output layer are composed of with these data sets. So these data sets are called the IMNIS data sets. Specifically, this one is the number IMNIS data set, and this one is the fashion IMNIS data set. So for both of these, in these data sets, there are around 6,000 images that are each 28 by 28 pixels. Now, if we look at the input layer, we're going to have 784 nodes. So 784 of these circles that you see. And the reason for this is because in both of these data sets, when we want to input, what we need is to flatten these images. And how we're going to do that is by flattening them into a 1D tensor, we're going to be multiplying 28 by 28. If you calculate this on your calculator, you don't have to actually, but if you do, you're probably going to get 784. So we're going to have 784 of these nodes, and one pixel corresponds to one node. And then we're going to have multiple hidden layers, which are going to be performing computations. And at the end, we're going to be having 10 nodes in the output layer. The reason for this is because there are 10 classes, which means that there's 10 possible outcomes for the data to be. So in this case, it can be numbers from 0 to 9. And in this case, it's going to be 10 different clothing items. So it could be any of these. And that's essentially what makes up my feed-forward neural networks. So now that we've gotten a bit of background information, let's get into my code. And if you want to follow along with my code, since I'll be going incrementally in small chunks, you can view my entire project on my GitHub repository, which is linked in the description. So this right here, all of this is the code that I have for my feedforward neural networks. And I have one Jupyter notebook for number MNIST and the clothing MNIST. So I'll be going through them, and there's so many similarities, but there are some specific differences that I will be pointing out. So this code is in VS Code, and there's many perks of using this platform. However, one issue is that I won't be able to show you images, as when putting images on a Jupyter notebook in VS Code, it shows up as an error. So I'll be switching my windows, and although it may be a bad transition, let's look at it from an optimistic manner because it is better than nothing and will help you visualize the concepts that I'm talking about. So our code is split up to 6 crucial parts. The first one is importing the libraries. So in this code cell you see right here, we import the libraries. Matplotlib and helper are used to plot graphs and data that we'll be getting from our model. And then, since we're using PyTorch to code out our feedforward neural networks, we need the torch package and some of the contents within it, such as NN, which will be used to build the network, and Optim, which will be used for optimization algorithms. We also need to take the torch vision library and import the datasets and the transforms. So the datasets are the MNIST and fashion MNIST datasets, and the transforms is what we will be using to normalize the data, which brings us to our second step, which is to normalize the data and download and load the training and testing data. So first of all, we want to normalize the data. And the reason for this is because we want to make it more convenient for the model to process and have a higher accuracy. So first of all, we need to convert all the data that we have into a tensor. So the reason for this is because right now the pixels are at a range from 0 to 255, which is the RGB standard. But to make it easier to process, we want to make it from a range from 0 to 1. So that's what the tensor is doing, that function. Then we're going to be normalizing the data. And essentially, when normalize is set to true with this function, it means that the image data will be grayscaled. So since normalize is equal to true here, this image is grayscaled. Then we want to download and load the training data. So in this instance, we have train set and test set and train loader and test loader. And they're pretty analogous, but there's one part that's different, and I'll be mentioning that. So for train set, we have the data sets that we get from the Torch Vision library that we imported here. And then we include the path to the file for the data, if it's being downloaded or not, if it's being trained or not, and we're going to be applying the transforms to normalize the data. So this is the same, and this is pretty much the same, except here we have train set to false. If you haven't guessed it, it's because this is testing data, so there is no need for training, and this is why it's set to false. Other than that, the train set and the test set are pretty much the same. Then for train loader and test loader, we're going to be taking the data from the data set. We're going to be setting a batch size of 64. So a batch size, for your information, is the number of samples that are passed through the network at one time, which is one epoch. And an epoch is one forward and backward pass through the model. Then we're going to be setting shuffle to true. This means that the order of the image data is going to be switched every time, and this allows for more accuracy of the model. Because if we train the model again and again in the same order, it would, in a way, memorize them. So think of this as you're writing the test, you learned all the definitions. If you learned all the definitions and they're in the same order, it's going to be easier for you to remember that, oh, this definition was right under this. That's why the answer will be this. But since it's shuffled, your accuracy will be higher. And to test this, we'll run this to the data loader. And this will give us a number. So in this instance, this is a 5. And remember that this is grayscaled. Now for the clothing imness, it is pretty much the same, except the path file here for the train set and the test set are different because this is another data set. And so when you run this, it gives you a clothing items. So this is some sort of robe, this is a shoe, and so on. So those are our first two steps. The next step of this process is to build the model. And here, the code is fairly simple as long as you understand the neural network architecture. So here we define the layers that we need, and we define the model here. So, three things that we need to ask ourselves when considering how we're going to come up with the model are how many layers there are, how many nodes are there in each of those layers, and what transfer or activation function is used in each of these layers. So, if we go back and see, this is the neural network architecture that we need for the number MNIST dataset. So as I mentioned earlier in the video, you need 784 nodes for the input layer and 10 output nodes for the output layer. And then in the middle, I have two hidden layers. This one has 256 nodes. This one has 128 nodes. Now, along with this, as this picture portrays, the model needs the ReLU and softmax functions, which are acting as activation functions in the neural network. So the ReLU function, what it does is it cleans up these numbers that we have here. So if the number is negative, it makes it 0, which is already done here. And if it's greater than 0, then they remain as they are. And then the softmax function is very important when it comes to expressing the probabilities of each image being a certain class. So those are the activation functions. And along with this, in our model, we also have the dropout function. So the dropout function is used to prevent overfitting. So this is when we train the model and it becomes too aligned with the training data, but then it doesn't do well on the testing data, which can be detrimental for the model and the algorithm itself. So please note here that the number MNIST has two hidden layers, but in the clothing MNIST, it has three. So you're probably wondering, well, why in the world does this have two and this have three? Well, the reason for this is, you see, the clothing dataset has very complex images as compared to the number MNIST dataset. That means that since they're more complex, the accuracy has to be higher. And the way to do this, one way, is to add one more hidden layer to make the neural network deeper. So that is the next step. And if we run this, you can see the model that's printed out. And the same for the clothing MNIST, except it's going to be longer since we have an extra hidden layer. The next step in this model is to train it. And the way we're going to be going about doing this is we have a set number of epochs. And this is for loop that goes through 30 times. So 30 times we go through the training data, we go through the testing data, and we train and test the model. And after that, we print out all of these, which I'll be diving deeper into. So first of all, we need to train the model. And the way to do this is to first define the total amount of loss. Now, the loss, the way to think of this is, let's say you're shooting a three-pointer for the first time. Now, I'll tell you that you're obviously not going to get it in. Well, you might, but you're not Stephen Curry, right? You're not going to get it in every single time. So, what's going to happen is, let's say you airball the first time you shoot a three-pointer. Then what you're going to do is, first of all, you evaluate the loss as the shortest distance between the ball and the net. So you see how far off you were. That's the loss. So you want to minimize the loss. In other words, you want to increase your accuracy. And so what you're going to do, you're probably going to maybe change your position on the court to shoot the three-pointer, you're maybe going to change your shooting form, or you're going to do something different that would help you to train and minimize your loss. So this is exactly what a model is doing. It's trying to minimize the loss. And the way it goes about doing this is, first of all, it gets the images and labels that you have from train loader. So the images are the images in the dataset, and the labels are the actual answer to the images that correspond to each other. Here what we're doing is we want to change the images from a 2D tensor to a 1D vector. So let me show you an image to explain this. So this right here are 2D tensors, but they need to be a 1D vector. The reason for this is, as I mentioned, you want there to be pixels that are run through the model, right? Because one pixel is one node. So if you have it in a 1D format, you can easily give each single pixel a node. And then after that, what you're doing is you're setting an optimizer.zero gradient. And what this is doing is every single time this loop to train the model runs, we're taking out the gradients. And the gradients are the change in the weights. So the weights, as you see on this model, the weights are how strong the connection is between these lines that connect the nodes. So the gradients are the weights relative to the error, or the change in error actually. So that's the slope. And clearing the gradients this way from each other, it's necessary so that the results don't collide with each other and cause very hard to deal with errors. I'll tell you that from experience. After that, we're running the images through the model that we defined here, and we're putting it in log PS. So it basically runs all the images through the model and gets the probability of each class. So this is an example, and this is showing 10 items in the list because there's 10 classes that could be the output, and it shows the probability of each. After that, we set the loss, which I explained earlier. And with the loss, you use it with the criterion. So the criterion is over here, and it's set with the NN module that's negative log likelihood loss. So that's NLL loss. This finds a difference between what the image shows and the label says. And since it's using this NLL loss, it means that the loss will always be negative, and the closer it gets to -1, the more accurate it is. And we'll be looking more into that once we actually run it. And then at the end, the total loss of the entire mini batch is divided by the batch size and added to the total training loss. So that's what happens. That's why we need this right here. Now, before we do that though, once we take the loss, we have to do backpropagation. And backpropagation runs through the model backwards. And then you change the gradients of the model so that you can optimize it, hence the name optimizer. And here what we're doing is we're taking the model's parameters and we're applying the learn rate of 0.03. So this is a slow learn rate because the way the model works is, think of it as a moral story of the hare and the tortoise. The slow and steady wins the race. And in this case, the race is how high can you get your accuracy. So that's how training the model works. And after that, we need to test the model. So that was the training ground. Now when we're testing the model, we have to see how the model does with unseen data that we have in our testing set. So the training and testing code blocks are fairly similar, but there are some changes and some more syntax that is required to print out the results as well for the epoch that it's running through, the losses, and the accuracy of the model when testing. So first of all, we have these two variables, the total testing loss, which is similar to what we had here, and then the test correct, which is going to be used to determine the accuracy. So since this piece of code is for testing. We don't need any gradients. And so here with torch.noGrad, we are turning off the gradients. And similar to this, we don't need dropout here, right? Remember, dropout was to prevent overfitting, and we only need that for the training. So we don't need it for the testing, and we turn it off. But then we do turn it on again, so that once the loop starts again, it uses dropout, then turns off, then turns on, goes to the training, and so on. This way, we don't use dropout for the testing. So here again, we convert this, we flatten the image, that's what the process is called, and then you're similar with all these steps. So we won't go too deep into this. Then we use the PS variable, and this gets the probabilities of the images. And yeah, you can also substitute log PS into this since it's pretty much the same. Essentially, we're running the images through the model and we're getting all the class probabilities. Then we use the top P and top class variables with ps.topk. And what this does, with number 1, it gets the top probability, which is the class that is most likely to be the output. And this is getting all the probability values and all the indices, so the index of which class it actually is, so which handwritten digit is it, and then this is for all the images. Then here we're comparing with the variable equal, and this will be either true or false. So you're saying that if the class is equal to what the value for the is if the class is what the label says. So if the top class is equal to what the answer actually is, then you would set the equals to true. And here you find the means of the zeros and ones to find out how many you actually got correct when running through one epoch through this batch. And then after you want to add to the total train losses and total test losses, and this is after we're done training and testing. So once we add this to this entire list, what we're going to do is we're going to print out, first of all, the epoch that we're on. So there's 30 epochs, so it's going to print out like epoch 1 out of 30, 2 out of 30. Is going to print out the train loss, and is going to print out the last one in the list. And same thing for testing loss. So it's going to print out this for every single epoch, including the test accuracy, which is essentially the amount you got correct over the length of the testing data. And that's essentially finding the average accuracy of the epoch. So if we run this, and I won't actually run this right now because epochs take a lot of time to train. Like right here, this took 3 minutes and 44 seconds. So I don't want to torture you and make you wait for 3 minutes or 4 minutes around. But this is what happens. So it starts off with the test accuracy of 61%, which is not that bad, but it can do better. And you can see that that does happen because the train loss gets closer and closer to -1, and the accuracy gets closer to 1. So if we convert this into a percent, it's essentially 96%, which is great. Now with the clothing imminence dataset, the accuracy starts off with 28.5%, and the training loss is fairly high. But then again, similar to the number imminence, gets better. Now for this one, the accuracy becomes 73% around, and the testing loss does become better. But then the accuracy is very low. Why? Because as I mentioned, the images in the clothing image dataset are very complex. So it becomes hard to essentially test it and train it with a very high accuracy. And this is where CNNs comes in. And I'm really into CNNs and I'm diving deeper into them so I can make more projects with them. And if I do make a project with the clothing image dataset, the accuracy is going to be way higher because CNNs are used for image classification. Now, this was just a foundation for CNNs, which is why I did these projects driven by my curiosity and ambition. So after you do that, you want to print out the plot. And the plot uses matplotlib. And you can see here that the training and testing loss is decreasing over the amount of epochs. Same thing here, they're decreasing over the amount of epochs. So the last step is visualization. And we know that our model has a low loss and high accuracy, but let's actually look at an example of this from the testing dataset. What we do here, when we run this, the images and labels in the test set are split up. The images are flattened, and we're running the images through the model. After we use this helper library that we imported at the very beginning, and we classify by looking at the first image in the test set, and then we look at the probability of it being every single class. And then we also print a label to see if they match up. So in this example, we have the number 4. So this is one of the images, actually the first image in the data set when you run it. And this actually switches every time because, as you remember, we set shuffle to true. After this, you see that the class probability is 100% of being 4. And we see that this is right, meaning that it had a high accuracy in this case. Now let's look at 3. Oh, we can tell that it's 3 by the handwritten digit, and so can the computer. Now if we look at the clothing items, we can see that the number 7 and the 7 here match up, which means that the classes match up. Now, if we look here, 9 and 9, they match up as well. 1 and 1, they match up as well. So we know that our feed-forward neural network models are doing very well. That was the demo. It was a pretty long demo, so it was more like a tutorial of my 2 feed-forward neural networks that classify, first of all, clothing items and handwritten digits. So I hope you enjoyed this video and learned some valuable insight into AI, which is a revolutionary and emerging field that you should definitely gain some skill set and expertise in. So I really hope you enjoyed, and if you did, please don't forget to like, subscribe, and turn on post notifications.